On behalf of the Bangalore Chamber of Commerce, we welcome each one of you for this knowledge sharing session on additive manufacturing significance in Indian manufacturing. Before we could start, I will request all of you for a minute of silence for the uh, for the people who have lost their lives due to COVID, and then also the frontline warriors support that we have done. A request for a minute of silence.
Good afternoon.
Thank you all for your cooperation. Let's start this session. This session has been organized under the aegis of Manufacturing Expert Committee of BCIC. We would like to specially thank Mr. Prakash, Chairman of the Manufacturing Expert Committee of BCIC, and also who's the Vice President of Toyota Kirloskar Auto Parts. And also we'd like to thank Dr. Devarajan, who's a mentor of the Expert Committee and Senior Vice President. And also a special thanks to Shiva Ganesh, who's a member of the committee and who represent from Farnok, India, for curating this session for the benefit of our members. The speaker for today's session is Dr. Vishwas R. Puttige, Business Head, AMAC Solution Part, which is a part of the AC Micromatic Group. The objective of today's session is to facilitate manufacturing industry, especially who are in the metal cutting know-how on additive manufacturing, their scope, application, and significance. And we are sure that after today's deliberation, the session, the key takeaways will be on fundamentals and significance of additive manufacturing, the application area of component manufacturing, some case studies on the real application, and benefits, need, and future compared to the traditional metal machine processing. The session will be moderated by Mr. Prakash G, Chair of the Manufacturing Expert Committee of BCIC. On behalf of BCIC, we express our sincere thanks to Dr. Vishwas for accepting our invitation to address on this important subject. We would also like to thank all the participants for joining in today's session. We request all the participants to kindly mute your mic and webcam option. This will enhance and keep the bandwidth strong, as well as avoid any disturbance in the background. Please post your questions in the chat box and the speaker will respond accordingly. Or you could raise your hand, for which the speaker will be able to seek your inputs or questions. May I now invite Mr. Prakash Ji to set the context and also moderate today's session. Thanking you all once again. Over to you, Prakash sir.
Thank you, Prithvi, and once again welcome Dr. Vishwas for this BCIC first of all to the BCIC platform, and also thank you very much for accepting our invitation to conduct this kind of a session. And just to give a background about BCIC and manufacturing, we are probably 800 plus companies. Members of the companies are the members of BCIC, ranging from auto components to aerospace to pharmaceuticals, FMCG, and also I think even the range of industries. That means to say their turnover, MSMEs also included in this. So and also consulting. So you can imagine the kind of diversity the BCIC has got. So there that means to say that the members are also very keen to know new things, different developments which are taking place in the field. And specifically, this session we have organized basically to make our members aware of the opportunities which exist in the additive manufacturing. And as you know, I think Before I introduce the speaker, I will just touch upon the additive manufacturing field as such. And for most of the people, it is like just give a simple, in a simple sentence, we say what you see is what you build in additive manufacturing. So additive manufacturing is known in different words. Actually, it is like 3D printing, rapid prototyping, rapid tooling. It's like, I mean, various words are there. I think of late it has become standardized as additive manufacturing. And so far we used to know, it's every time we used to make a design, we used to think about manufacturing, design for manufacturing. But this additive manufacturing has actually made a complete paradigm shift in looking at thinking as manufacturing for design. And additive manufacturing is a complete ecosystem. It is not just for cutting the metal, or removing the metal, or adding the metal. So it consists of everything. It consists of software, materials, design, every aspect of it. So, and very nice word we talk about additive manufacturing. It is basically complexity is for free. You know why? Because most of the components, when you have a very high complex material or a complex shape, we think that it is very difficult to manufacture. That's why the cost of manufacturing is very high. But in this case, it is not like that. It is going to be less. When you have a complexity, more complexity, less the cost. Similarly, it is about mass customization. So, any type, each, I think you have seen the people using the ear sensors, no? Those who have inability to hear, is all mass customized. So from that angle, additive manufacturing has been a very big gift to all of us, where we are moving towards what we call as a high variety, low volume manufacturing. And more so, I think additive manufacturing also helps in what do you say, very complex material. That is to say, very difficult to machine, in the sense that titanium, nickel, and cobalt have very difficult to machine in a traditional manufacturing, while in additive manufacturing it's very, I don't say it is very easy, but it is made easy. Right. So with that background, and we have with us Dr. Vishwas, and Dr. Vishwas has been a, you know uh, he's a business head of Amaze Solutions. Basically, it is additive manufacturing ACE. I think I can read it like this: ACE, Additive Design and Engineering Services, 3D printing of metal parts and finish to desired size. Prior to this, he was ACE Manufacturing Systems R&D and OSD head of business, and he has also worked as a research scholar in Australian Defence Force Academy. He comes with a doctorate in philosophy in control systems and automation from University of New South Wales, and also Masters of Engineering in Systems Engineering. And he has done his basic engineering from BCIC in Electronics and Communication. So this kind of a, I mean, highly resourceful person, highly knowledgeable, and now he is into the business. So I think what is required right now is this kind of people who actually lead the industries. Now we are having a right person in the right place. So over to you, Dr. Vishwas.
Thank you, sir. Thank you so much. It's a great privilege and honor to be here, to be presenting to this August gathering. I see some very familiar names also. Thank you so much, BCIC, for giving me this opportunity to be presenting. For the sake of bandwidth, I hope I can turn my video off and I can continue with the presentation. Is that okay, sirs?
Yeah. Please go ahead.
Okay, so without any much ado, I'd like to get started with the presentation here. I hope my screen is visible.
Yes, visible. Please go ahead.
Okay, so it's today, as sir, you brought out some very interesting points here about additive manufacturing. Very beautifully summarized the technology itself here. Now, as you rightly said, additive manufacturing has been changing the face of manufacturing today from a long time actually, and in these past 5 to 8 years, it has gained a lot of momentum. Especially after some of the patents were opened up, after some of the prominent manufacturers, leading manufacturers globally realized the true potential and started leveraging on those potentials and started using it. So what is really interesting is additive manufacturing is not limited to a specific type or material or concept. It is one of the fastest growing and evolving technology today, where people are trying out all different types of methodologies, technologies in this specific space, and trying to bring out and utilize that for their purpose. It could be different aspects. So I've put together the presentation here in this format, where we'll talk about why additive manufacturing, why are we here today, why are we talking about this subject, then feasibility, what sort of components, where do we find additive to be more feasible and where not, and different technologies and additive, we'll touch on that. I brought up that just a bit. And then we'll also look at from a manufacturing design perspective, what has to change and what needs to be kept in mind. We'll touch on that. And like you rightly said, sir, we'll touch on multiple case studies. We'll touch on different markets and case studies of additive, which will give you a much better understanding of what is in store for us in the future or even in the present. That's how I've put together our presentation. So we'll get started, sir. Why additive manufacturing? A few of them you rightly mentioned, sir, but to start with, what is really different or beautiful here about additive is it's actually the natural way of manufacturing. Today, additive manufacturing takes you much closer to nature. If you look at anything outside around us that is made by nature, it's been done the additive way. For example, a plant, a tree, an animal, our human body, it's all done as a monolith structure, where actually material is grown, or human body is grown progressively, portion after portion, in a single piece or in a single entity. Now, in a similar way, what additive does is you constructively add material to the exact shape or size that is required, and put the part together or the assembly together. So additive helps us take us more closer to nature, also because the kind of wastage that we would see in additive manufacturing is far lesser compared to our conventional methods of manufacturing, which involves a lot of subtractive process. So this is one interesting aspect. And today, one of the most popular methods is the prototyping, which we've known, I think, for the past 30 plus years. People have been exploring additive manufacturing. In fact, this terminology also until recently was very popularly called as rapid prototyping. Which for 20 plus years people called it as rapid prototyping, and even today some of the people use it synonymously with additive manufacturing, because the technology was mostly popular for prototyping. However, today things have changed. The technology has come a long way in just limiting itself to making prototypes, but also being suitable for production environment. So, but however, even in India today, the most popular domain for this subject is prototype developments. So it not only allows you to develop components, but also assemblies much faster compared to the conventional routes. In many cases, today we've seen the whole manufacturing scenario is such that where people want things very fast. What used to be a 5 or 6 year product development life cycle has probably shrunken to 1 or 2 years today. The expectation of newness is very short-lived. People get used to seeing something which was launched 1 or 2 years ago, and they want to see newer products. So, which is very beautifully brought out by our automotive OEMs, who bring out newer vehicles much more frequently today. To support all this, one of the technologies that has been very beautifully playing a role is additive manufacturing, because your prototypes can be developed faster, and it accelerates the whole design process by making it giving speed to the design and development. So, of course, time to market is what I brought out, and then multiple of these parts today, both from an automotive and other engineering perspective, are being 3D printed and are being used. So that's another very interesting case. Now, sir, you brought this exact term, complexity for free. I'd like to illustrate this terminology of complexity for free in the form of a graph here. So what you can see here beautifully is a graph which shows you complexity versus cost. So we all know that with the increasing complexity of parts, the cost increases almost exponentially. So something that is very complex, be it in shape or size or intricacy or criticality, would call for either more number of axes of manufacturing or more stages of manufacturing, or more process. I mean, it becomes more process intensive, which is why the cost ends up becoming more and more. So, which is very common. We all understand this subject. Now, when you bring in additive manufacturing, the interesting aspect is beyond a specific point, additive manufacturing ends up becoming almost free of cost in terms of the complexity, which means irrespective of the design or the shape or the size of the part, the only thing that matters is the volume or the printing time and the material that gets consumed. So if you say 200 grams or 300 grams of aluminum that has to be printed in whatever shape, it could be a plain block of aluminum, or it could be in a form of a very intricate aerospace part that gets produced, the cost of manufacturing would be almost similar. So that gives you a clear analogy as to how additive really supports complex part manufacturing. So wherever you see higher surface area, wherever you see more complexity, additive ends up taking over beyond 3D printing. Beyond the conventional manufacturing, and it becomes more and more useful. So you see that red line, that is where the break even of complexity happens, where you decide beyond a specific point, for very specific applications like aerospace, additive manufacturing or 3D printing ends up becoming the most suitable technology of manufacturing. So that cloud that you see, which shows complexity for free, ends up showing you how this happens. And irrespective of increasing complexity, the cost remains the same. That's the analogy of this graph here. Now, another interesting aspect is part consolidation. So you can see a beautiful example here where this was courtesy General Motors, where for a seat belt assembly, as you can see here, they've gone ahead and done part consolidation techniques by using some design for additive manufacturing, wherein individual pieces, about 8 individual components, were all integrated into a single part. Not only did this make it 40% lighter, but it also made it 20% stronger. So you can see the monolith structure that is produced by 3D printing on the right-hand side. Now, let's leave the cost part of it aside, but this is what they decided to do for a high-end automobile of theirs, which they felt would bring in not only reliability, but also achieve a lot of your GD&T aspects. So today we all know finally an assembly is sum total of all the parts that we put together. So your stack up tolerances end hitting you when you have individual parts which have to be made so critically. So in this case, since it's a monolith structure, your overall accuracy can be made in a little more simpler way, as opposed to producing parts individually with your geometry tolerance maintained and then putting them together as an assembly. Also, the reliability increases because fewer number of joints, better is the reliability. We all know that from our design school. So this is an interesting aspect which is happening more and more, and it's being accepted very well. We'll see some more live cases going ahead. Sir brought out this again interesting example. So mass customization. So what does customization mean? We all know a tailor, typically what he does for us is a customized clothes stitching, as opposed to what is available in a ready-made garment shop. So a very beautiful example, like Sir mentioned earlier, is customized hearing aids. Today, we all, I'm sure we don't know the fact is that any hearing aid that either our older people end up getting, they're all made customized for the specific person's ear and ear size and shape. So they're all 3D printed. You can see one on the top left corner, the orange color image is hearing aids which are made specific to every person's ear lobe or penna or the internal aspect, which so that it fits in fine, as opposed to what used to be generalized one size fits all kind of a concept. So this allows it to be sitting, and the fit and function does a much better match here when it's a customized one as opposed to a generic one. Similarly, the bottom, what you see is a dental crown. So today, another interesting aspect as we see is a dental crown. What used to happen in the form of a mold that is taken in a wax or another softer material, and then a crown is manufactured. As opposed to that, today dentists are using intraoral scanners, and they create a 3D model in a very short time, and the lab technician prints multiple of these dentures. Each of these are for a different patient. With a small digital signature, people are able to, the lab technicians or these manufacturers are able to make these dental crowns in high volumes, but they're all customized parts. So imagine something like this becoming mainstream for other applications also, where you'd have each person's specific part or maybe an assembly being done to the taste of every individual, but produced in high volume. So today, what you see is on the right, variety is free in printing. So which means, again, it could be my tooth or my colleague's tooth that is being printed. It doesn't matter. Variety could be as many as the number of components, which means a batch size of one. A batch size of one is also possible. Hello, am I audible?
Yes, yes, you're audible. Please go ahead.
Okay,
You're
okay.
saying.
Yeah, okay, sorry. So the batch size could be as small as one, and manufacturing can happen in large volume. So that's the beauty here, and that's the interesting aspect of mass customization. Another interesting point here, which summarizes the whole thing, is in terms of volumes also. As you see, the bottommost is rapid prototyping, which is the large volume of manufacturing. Which is the largest in terms of adaptation, where you have low volume parts, which you'd want to make directly from CAD. 3D printing is suitable. And then part replacement, which is reproduction of parts to avoid complex manufacturing process, where you'd have heavy investments in terms of your tooling. All that can be avoided by printing parts where you have smaller volumes that are required. And part consolidation we discussed. And of course, there's a topic called as DFAM or DFAM, which is designed for additive manufacturing, where you optimize the parts to suit 3D printing. We'll touch upon that going ahead. So that was the why additive manufacturing subject. Now let's look at the feasibility perspective. When we say feasibility, now what are the parts that are feasible? Though this sounds very interesting, though we go ahead and tell almost any part that is required can be 3D printed, anything that can be designed can be manufactured, it may not be the case all the time, not necessarily. There are certain criteria, there are certain qualifying aspects which need to be considered before we decide if 3D printing is the most feasible route. One typical analogy that we give to our customers is this here, where imagine a situation where your volumes are low, what you see on the left side, and the geometries are machinable. You have these geometries machinable, then CNC or the conventional route is the most popular one that we would choose. However, if your geometries are not machinable, but your volumes are low, then you can directly print these parts that would be more viable and cost effective, which you see on the left side lobe. Whereas if you have high volumes and your geometries are machinable, in such situations, we have things like die casting, which is a more popular and more suitable route for us to go forward with. However, if the geometries are not machinable and your volumes are high, as you can see on the right side, rightmost one, you can use investment casting and make those patterns using 3D printing. What is very interesting is your complex patterns to be able to reproduce in terms of your castings or your parts can also be 3D printed, which otherwise again needs conventional manufacturing. 3D printing comes in handy. So it's not for one specific aspect, but it can be used for a wide set of activities or multiple aspects here from manufacturing. So this is one aspect from a feasibility perspective. On the same lines, so this here you can see a comparison between subtractive and additive manufacturing. So on the top, what you see here is additive manufacturing, and the bottom image on the left side is subtractive manufacturing. So you can see, as I explained earlier, conventionally, we to make a part, as you can see, like a spear here, there's a lot of subtractive material or waste material that gets generated. You mill it out and then you scoop it out to get the actual part. Whereas with 3D printing, with very minimum wastage, you're able to get your final part out because you're adding just enough material to get the part to its final shape. Now, on the right side, what you see is a comparison. Again, we saw cost versus complexity, but at the bottom, I'd like to refer to cost versus number of components. You can see when the volumes increase, 3D printing may not be very feasible, especially because you end up having your costs generally are a little on the higher side. Whereas when conventional manufacturing, when your volumes are low, your investment towards towards the development cost, or the maybe your investment towards making dies and fixtures and your patterns, all that is going to be expensive. So 3D printing, there's a tipping point beyond which, in terms of number of components, 3D printing may not be very suitable, unless again you have varieties increasing, complexity increasing in the specific parts. So again, this is another interesting feasibility perspective that is there, which can be used to decide when 3D printing will be very useful for manufacturing. So this is basically the process flow to give you an idea as to how 3D printing happens. So you can see from your design stage and stage 1, what is shown here as a 3D CAD or a 3D model development. We convert it into STL. Basically, STL is a format of your 3D model, which converts any volumetric part into triangulated surfaces, as you can see there. And those triangulated surfaces are further sliced into multiple layers, like you can see in stage 3. So this is an exaggerated version of showing big thick slices, but in reality the slice layer thickness could be anywhere from 30 microns going up to about 100 microns, and each of those sliced layer data is fed to the printing machine, which will fuse the layer one to another and creates a very strong bond, making it into the solid part. So this is how the part is formed. And of course, there could be small finishing activity, which is shown in the form of a surface finishing hand tool, which gives you the final shape. So this is a generic process flow that is there for the 3D printing. So this gives you an idea of the feasibility perspective. Now let's look at different technologies that are there in additive. Though this looks like a big image here, just to give you on the left side, I'd like you to look at the different materials currently, the most popular materials that are there for 3D printing. Things like wax, plastic, sand, metal, ceramic. These are some of the more popular ones that are being used. Other than these, there are many more that are happening in terms of biomedical or tissues and organ printing. There's food printing. There's a lot of interesting aspects that are going on in each of these areas, and a lot of research going on. But specific to industry, when I refer to here, we have an interesting aspect. You can see at the bottom, what is shown is from a durability perspective, surface finish perspective, and detailing perspective or application perspective, lower and higher. There's a distribution which shows what technology has found more application or has found more suitability. So these are some of the prominent technologies that are there today, which is stereolithography, polymer jetting, binder jetting, fused deposition of modeling. The FDM technology is the most popular in terms of plastics or polymers. These are again more popular for hobby or small desktop printing also, which you would find in a lot of manufacturing areas or small education institutions also. Other aspects like laser melting is the most popular from a industrial acceptance perspective. So laser is the power source there, and in the other example we have EBM or electron beam melting, where the laser is replaced with an electron beam, and that used as a power source. And then I suppose we have laser sintering, which is more popular for the non-metallic materials of printing. And there's multi-jet printing also. So these are different names, different technologies that have evolved in these past 10 to 15 years for 3D printing of materials. So we'll be happy to share more details going ahead, but the whole concept is how I explained earlier. The concept is all about layer-wise manufacturing of material, where material is fused to each other with an irrevocable bond between the material layers, so that it forms a full rigid, full solid part which is required for your final use. So these are some of the examples. I don't know if I mentioned sand printing today. There are machines which can print sand to give you better molds to make your core box or your parts to make it much more feasible, which otherwise is very difficult to manufacture using conventional process. You have multicolored polymer printers, which means you can print almost near life parts. In fact, a very straightforward transition has been by all our 2D printers. So all your printers in terms of 2D, like HP, Canon, we have people like Ricoh and all your 2D printer, paper printer manufacturers have upgraded themselves into 3D because it's a very logical diversification for them from taking it from what they did on a colored material on a paper, adding the third dimension to the whole manufacturing space by giving it by doing what they've done. So polymer is again very popular, but mostly for applications which are not very industry specific. Then ceramics, again, not only for interesting, aesthetically good looking parts, but a lot of high temperature applications. Ceramics is drawing a lot of attention. We have graphite being printed, and of course, metal is well known. One of the latest is diamonds that are being printed. Of course, these are not necessarily for ornamental purpose, but these are for your cutting application. We all are familiar with Sandvik, who's been doing diamond cutting tools. Now they're the ones who've gone ahead and printed diamond for, again, some of the high-end cutting applications where very high levels of hardness and toughness are required. So like this, people have been doing different materials. These are again some of the more popular ones that have been shown here just for illustration purpose. Now, this is again an animation which shows you how the printing technology works. You can see powder being spread by the spreading unit, where after spreading there's a laser which melts it. This is again more popular for polymers or metal printing, where you have metal powder which is spread on an existing plate, and the laser melts that powder in a selective area as commanded by the program or the controller, and that forms that irrevocable bond or the fused part. So you can see on the left side what is happening is a part is printed almost 70-80%, and you can see it is sitting in the middle of a cake of powder. So the melted part is the solid part, but around it we have complete powder which is surrounding this, because it forms it is formed in a layer by layer way. So this is how it is. So you can see the layer thicknesses, accuracy is again, this is something that is that would be of interest to you today. The parts that are printed in this way are not necessarily fully finished in terms of functional use. It is much better than near net shape. It can give you close to 100 microns tolerance levels. So for parts which have either open tolerance or with minimum tolerance requirement, these would be very suitable. But for something much more critical, you would still need that final finish skin cut to give it that final accuracy or get that final dimension right. So that's the one small missing aspect or thing that needs to be still worked on. People are working on that further. So what you can see here is again another similar video which will show you the metal printing that's going on. So here, this is something that we've been printing in metal. You can see there are two lasers which is printing where metal powder is existing on top of the previously printed layer, and the laser is melting it and bonding it to the part in the previous layer. So once this happens, in the middle, what you see here is the middle area is the part which is sitting in the middle of a big cake of powder. After printing, it gets surfaced out, and the part around the powder around it is removed and extracted and recycled. What you get is on the right side, you can see a fully finished part, which is in this case is a specific die of a customer that we printed for a specific application. And again, the interesting aspect is it doesn't need any further post-processing. It can get separated either with a hand tool or a bandsaw or a wire cutting machine, and then used for its final application. So this is basically how the concept works, how the technology works, and how the material or the parts are produced using 3D printing. So all it needs is a 3D model. So you can take from a design stage or from your design desk all the way to a finished part in a matter of few hours. So we have some very interesting cases which we'll share and tell you how we've been able to meet some of the urgent demands in the industry in a very short time using 3D printing. So from a material perspective, this is again one of the most researched areas. I refer to only metals here. So you can see some of the more popular materials that are there that are being printed. Materials like stainless steel, SS316L, 17-4pH, precipitation hardness steels. We have Inconels of different grades, 625, 718, etc. We have aluminum alloys of 2 or 3 different grades that are being printed, which are again very popular for automotive, aerospace, and other general engineering applications. We have different grades of titanium alloy, which are more popular in either defense or aerospace applications because of their strength to weight ratio that is there. We have maraging steel, which is more popular in die and tool making. So like this, there are different materials, and many more other high performance materials are being developed and being used for specific applications. And as I said, though the basket of materials are limited compared to what is available conventionally, what generally happens is people try to map each of these materials to see what would be the closest for them for their specific application, and then use that either by altering some of the process parameters in terms of printing, or as a post-printing activity in terms of any heat treatment or surface treatment aspect to bring it very close to what you would want to meet your metallurgical aspects or your mechanical properties. So this is from a metal perspective what we have summarized here. So moving on in terms of the DFAM or the design for additive manufacturing, what I explained. So what additive actually does is, see, additive will never be able to replace conventional in the form where if you're producing a part, say for 500 rupees, we will never be able to answer a question, can you do the same thing for 499 or 480 rupees? So it's not a direct apple-to-apple replacement compared to the conventional manufacturing. So which is what gives you the reliability or the feeling that it's still a very long way before 3D printing can directly replace any of our conventional manufacturing process. However, where you can bring out or leverage on some of the strengths of 3D printing or advantages of 3D printing, there people have been able to benefit immensely using 3D printing. And for that, what is necessary is this subject called as design for additive manufacturing, where one needs to unlearn some of their known technologies of design and relearn methods of 3D printing or methods for doing additive manufacturing. So one of the aspects in that is this: you need to understand how we can go ahead and do the 3D printing process. So in that DFAM or design for additive manufacturing, as you can see here, is a method where you need to understand how intricate shapes can be done without, or rather, how do you make either do things like weight reduction or part consolidation or any specific aspect that is required, like an optimization of design to bring out to meet your end goal requirement. So there are multiple aspects to design for additive manufacturing, but two of the more important aspect is what we would like to explain here. One of them is aspect called as topology optimization. So you can see multiple images here, multiple examples here. What is explained is one of them is modification. So topology optimization is basically where you go ahead and change or modify the topology or the geometry of the part to suit 3D printing, and thereby also meeting your end goal. So in certain cases, it could be actually very interestingly, if you actually do an analysis from your design for, say, structural optimization or thermal optimization or weight optimization, and you run it through a software such as ANSYS, invariably the design or the shape that comes out as an output is something which is much more lighter, much more, in fact, very complex to manufacture or even comprehend to manufacture. But for sake of manufacturability, for sake of ease of manufacturing, we end up adding a lot of additional redundant material to this design so that it meets your feasibility requirement in terms of either casting it or forging it or any other process of manufacturing. Whereas with 3D printing, that doesn't exist. You can see some of these parts which have been optimized for weight reduction. So you can see this classical case of a manifold block wherein a weight of 30 kilo was reduced to almost 5.5 kilo by 3D printing. You might ask, is it worth that effort? But if you're looking at a case where you have a space shuttle which needs hydraulic elements for a lot of your open close valves, or your aerospace systems which need a lot of your hydraulic subsystems, and the weight matters significantly. For such applications, people are definitely willing to pay what it takes. And weight reduction is not just confined to either outer space or aviation industry today. Almost all of us are looking at weight reduction. Automobile manufacturers have been considering this. I'm sure sirs here would agree. weight reduction would directly lead to better fuel efficiency. So this is something that is on the minds. In fact, we're talking to quite a few electric vehicle manufacturers who've already started exploring either fiber or polymer printing for some of their structural parts of your automobiles to be able to make them lighter so the battery life can be increased more. So this is an interesting subject which is called as topology optimization. So here are some of the examples which are self-explanatory where weight reduction is illustrated very clearly. Another interesting aspect is this shown here. This is for an Airbus structural part. You can see on the extreme left the existing part, which was quite, quite light in itself, but still further it was modified by design for additive manufacturing to suit additive. Here, not only did it make it a little more compact, less material consumption, but also it made it lighter. So thereby, and also part consolidation was an interesting aspect. You can see each of those rivets or child parts that were assembled on that were eliminated because of 3D printing, because those features could be directly created in 3D printing itself. So that's the interesting aspect and strength of additive manufacturing and what design for additive manufacturing is doing. In fact, if someone would ask, okay, now let's start working on 3D printing, what is that one aspect you would want us to focus on? I'd say start learning aspects of design for additive manufacturing, start exploring this because it doesn't cost much. There are some simple software for each application, be it medical, be it aerospace, be it automotive. There are people who are working on it where you can explore design for additive manufacturing. So these are some more cases again for electric vehicle that people have been exploring to make cooling jackets using 3D printing by creating these artificial channels of cooling jackets. This I think was done by Honda Cars in Japan for their electric vehicle, where it obeys the rules of 3D printing or DFAM in their manufacturing. So another interesting aspect of this design for additive manufacturing is lattice structure. One is, of course, optimizing the structure itself, but second is to make it lightweight. So which is nothing but adding these perforations, which is called as lattice, instead of your infill of solid material. We add a lot of lattice structures here. This not only makes the part lighter, but also it retains, if not making it stronger, it retains the functional aspect of it. And in many cases, by 3D printing lattice structures, you're also reducing the cost, which means, as I explained earlier, one of the key considerations for cost is the amount of time you're engaging the machine or the material that you're consuming. Now, what happens when you're producing parts with lattice structures is you're spending less material and time on the machine to produce lattices. So thereby, reducing the cost also. So this is again another interesting aspect which is being explored by multiple of the people who are doing 3D printing or considering 3D printing as a method for part development, where they are infilling their parts with lattice structures like this here, as you can see. So this is just a summary of additive manufacturing or design for additive manufacturing. Now the interesting aspect which we'd like to explain are market segments and case studies. So multiple markets, multiple segments, exploring 3D printing. We'd like to show you some of them here, which are more prominent today. Some of them, as explained here, are medical, aerospace, automotive, tooling or die mold, and finally general engineering. So if you look at it from a distribution perspective, you can see today this is how it's been spaced out. We have medical being the largest, because of some of the very, very interesting aspects which we'll see next. Others are civil and aviation and defense, which take in more than 23% of total market share. Sorry, I lost my screen. Is my screen visible?
Yeah, your screen is visible. You can go ahead. You're right now at the share of system sales revenue by industry.
Sure. Okay. So other fields are like I said, automotive is about 11%, especially for some of the high-end applications of motorsports is where it's taking a lot of interest, and many other segments. So the more popular segments are what take away more than 50-55% are medical, aviation, automotive, and defense. So that's a segment-wise distribution. And from a distribution from a hardware perspective or the printing equipment perspective, you can see about 40% of the total landscape is metal machines. Then we have about 15% is desktop machines. And we have, when I say desktop, these are more like hobby machines, which are for small part development or protos, which are available even on Amazon today, which someone can pick up. And of course, you have the polymer printing, which are for industrial applications, about 26%, and the rest are the remaining aspects. So these are the more popular ones from a hardware perspective and segregation. Again, the different technologies in each of these that are there. So we will skip this aspect just to give you an idea, telling metal printing, especially the powder bed fusion one that we saw just a while ago, is the most popular technology and the most used in terms of industrial application by each of the sectors today, which we saw earlier. So that takes away at least about 39-40% of the overall market segment. So from a medical perspective, what is interesting is custom implant design. Today, one of the most preferred area is medical printing of these implants. When I say implants, I refer to things like what is shown here. You can see a cranial implant is basically a skull part. Today, when a person has a accident and there's a skull injury, and the doctor declares that there's a bone loss and he needs to be given an implant, invariably the patient's family has two options. One is either go for a standard implant, which is a titanium plate that was made out of conventional process, and to suit that existing plate, the good portion of the patient's bone will have to be chopped off so that can be fit in. This is very similar to telling 40, 42, 44 sizes of our shirts as opposed to a 39.7134. So whereas with 3D printing, all we need is a DIAM file which comes out of our CT scanning or MRI scanning tool, which anyway a doctor gets it done for the patient, and that itself is enough. In about 2 or 3 hours, a patient, in about 4 or 5 hours, you can have an implant that is ready for the patient, which is specific to that person's shape and size. So on a similar line, you can see kneecaps are being printed. This acetabular cup or hip socket with a lot of lattice structures are being 3D printed today, mainly because the uniqueness here is it allows bone tissues to grow through them. It's a process called as osseointegration, which means the bone tissues or the muscle tissues grow through these lattice structures, giving it a much better bond and less pain to the patient, and it lasts much longer as opposed to the conventional methods. So mandibular is the jaw joint of a human. Again, during any surgery or any accident, if this needs replacement, again through the same conventional, through the 3D printed route, one can be done. In fact, this is one of the most popular technologies we'll see today. And dental coping, you'll be surprised if I tell you there are more than 25 or 30 metal printing manufacturers or metal printers today who are producing dental copings all around the country, who are making it much faster. What earlier used to be at least about 10 days, 15 days to produce a crown, today can be done in a very short time. In about a day or two, this can be done because of 3D printing. So this is an interesting case for parts for medical equipment. So this is something that was done during the lockdown by us. One of the ventilator developers wanted some parts developed or made in a very short time. So what happened, we received an inquiry at 10 in the morning on a specific day during lockdown. Fortunately, we were working. And in about 45 minutes, a proposal was sent. The customer confirmed to us in about 3 or 4 hours, telling they'd like to go ahead with it. We printed the part, and next morning, 9:30, the parts were shipped. So in less than 24 hours from receiving an inquiry, the parts were shipped to the customer. So it just gives you an idea of what 3D printing gives you in terms of capability and the potential this has for any industry. So this was a specific case where there was an emergency and it needed that kind of attention, but possible for all other sectors also. Now, very interesting is this here, what we see, which is bioprinting. This is a game changer in the human life, where people have been successful in printing human tissues and human organs especially tissues where you can see ears, nose, and different skin parts, facial elements are being 3D printed today for especially in an aspect called as facial reconstruction of human faces, which is happening very well, where people either as a part of their cancer or a war victim who's lost a major part of their faces are being reconstructed, and it's being mostly from a cosmetic perspective. And another interesting aspect is artificial organs. Today, I'm sure you all know there's a long waiting of at least about 25-30 years and over many lakhs of rupees for any of these organs. If any one of us want a an organ to be transplanted, whereas if something can be 3D printed, they can be made in large volumes, and still these requirements can be met much better. So this is already be happening today. Even in Bangalore, there are people who are working on bioprinting, where some of these tissues are being reconstructed and 3D printed. So this is going to be a game changer going ahead. So from an aviation perspective, interesting cases here. One of the key aspects is weight reduction. You can see multiple of these parts that are printed here. What you see on the top right is a 2-kilogram part which was brought down to less than 760 grams with the same kind of functional use and capability, but much, much lighter. So this is a very interesting aspect. Then we have part count reduction, where assemblies are being 3D printed. I explained this earlier. So it's not just for prototype, but actual production. So you can see this left image, bottom one, which is a GE fuel nozzle. There are more than 50,000 of these fuel nozzles which are already flying in the air. So this is one of the most critical parts that have to be printed. You can see here 20 individual parts were integrated into a single piece, which not only made this part 5 times more durable, but also 25% lighter. On the right side, what you see is an engine called as Catalyst engine by GE, which is mainly for a single or a two-seater aircraft, which they are already commercialized and they're selling. In this case, you can see 855 parts were integrated into only 12 pieces, which means lesser number of bill of material items, better reliability, and lesser storage and much faster production. It not only gave them better fuel efficiency, but also reduced the weight further. So this again is not a prototype. It has already been proven, airworthiness done, tested, and today available for commercial applications. So this is what is happening. From a cost effectiveness, again, because as I explained in some of the cases, I'm sure you would have seen in aerospace, the buy to fly weight can be as low as 2 to 3%. When I say buy to fly, I refer to the input material weight for a aerospace part could be something as high as 10 kilo titanium block, but final part could be as low as 200 grams or 300 grams. So the entire remaining weight goes away as scrap, which goes at maybe 1/10 the price of the actual raw material. Whereas with 3D printing, you are able to manufacture the part with just enough material and then give it that final finish cut or finish machining and get the final output out. So that way it makes it much more cost effective for aerospace applications. And finally, on-demand manufacturing. Here, this is another interesting case where not just for aerospace, but even for automotive. On-demand means we refer to producing a part right in time only when it is required at the place where it is required. So in an automotive context, the interesting aspect is spare parts, which we'll touch upon in just a bit. But with aerospace, what is happening is they mean no inventory, no tooling. You are directly making it right when it is required. The parts are required. So that's the interesting aspect that on-demand manufacturing has. So these are some of the examples of different cases of parts being made, equipment being made. We saw the fuel engine. We have seen in fact, on Jan 25th, 2020, the engine which was made for Boeing 777 took off, and it's been flying today already with over 300 printed parts in that engine. So it just gives you an example telling that these are not just for prototype, but it's already come of age for full production also. So just an example, and I'm sure you all understand the criticality that aerospace industry has. So there's a beautiful timeline published by one of the industries which says going ahead by 2030, the aircrafts that will come out will be designed itself keeping 3D printing in mind, where every part or multiple of the parts will have aspects either internally or externally which will be 3D printed, mainly because of its lightweighted structures and airframes which will be more specific suiting 3D printing. So that's aerospace sector. Now from an automotive perspective, plenty of applications and advantages. Some of them are things like generative design, cost effectiveness, prototyping, spare parts production, and mass customization or individualization. So we'll look at just a few of them here. We saw this example earlier by General Motors. Now, invariably, when we get into product development or part development, what happens is we do a lot of design, then we subject it to some simulation or analysis to find out what will be the most suitable design. And we end up manufacturing only one or two of these parts because of the investment and the time that it takes to manufacture them. Whereas with 3D printing, the advantage is it opens you or allows you to produce many of these parts and put them to use, and then finally decide which is the most suitable one, meeting many of your constraints. So that's the beauty here. So this is what was done by General Motors also, where they produced each of these parts and put them to use and decided what actually works the best, rather than allowing it for the design to tell you what would be the most suitable one. This is an interesting case of Renault, where a truck engine for one of their newer trucks, they ended up using 3D printing, and where nearly 200 parts were reduced from their conventional one by using 3D printing. It's a nice video where you can see a lot of weight reduction happened and part count was brought down. So we'll quickly look at this video here, which shows you this illustration. You can see the before and after images of each of these, how weight reduction happened and by how much. Yeah, so like this, they were successful in doing, bringing out a lot of improvement in the whole manufacturing and bring the results. So that's that. I mean, like this, there are many other automobile manufacturers where they've tried to do either lightweighting or part consolidation for some of their high-end automobiles. But what is interesting, of course, okay, so more examples, more cases of some of these where parts either followed topology optimization for optimizing some of the aspects by either doing lattice structures, lightweighting, or consolidation of parts, again, especially from a development perspective, or very niche, small volume, low volume segment of your automobile. Now, the future of additive manufacturing is one of the aspects is mass customization. So you can see the image on the, I mean, see today the West is already talking about volumes high, but still varieties are very high. So a day may come when the batch size can reduce all the way down to one, where one would have to produce a part or an equipment which is very specific to that particular customer. You can see this image at the bottom where already there are manufacturers who are 3D printing eyewear equipment very specific to the taste, size, shape of a customer, so which is there. I'm sure you would have noticed even in the automobile industry, people have become very picky and choosy. Customers want a lot of specific requirements. They have either color combinations or something else which is very specific to their taste. Some of the automobile manufacturers have already taken the plunge into it, where you can see BMW's Mini is offering this, where they are going to be printing some of your softer cosmetic aspects very specific to your taste, where one can choose what would be more suitable for them, design them and get them printed and get that customized for their equipment, for their automobile. So like this, though in this case it might add a cost to it, but going ahead there will be a day when the costs are going to be coming down so much that it will become a very common thing. Today shoe manufacturers like Nike and Adidas have already started making shoes very specific to your foot size, shape and the pressures that you have, where they'll make you walk on a specific equipment which will capture all your data, and then they will print the bottom sole and you can choose what you want as an upsole skin of it, and then they will manufacture that and ship it to your home. So such things are already happening in some of the commercial more popular kind of equipment. I'm sure for some of the common ones also the day is not far where we will have to mass produce parts, but they're all going to be customized for specific requirements. Another interesting perspective or an aspect is on-demand component manufacturing. So as I explained earlier, today there are some automobile manufacturers in the West who have a commitment to their customers selling as long as they would the equipment would be in use. So for example, a Daimler truck or a Mercedes-Benz car, if it's 30 years old, there's a commitment by the OEM telling we will keep spares as long as you continue to use the automobile. So when they have this commitment, they also end up having heavy inventory of spare parts, few billions of euro worth of inventory, because they have this commitment, so they can't keep customer waiting. So they end up stocking them in different parts of their warehouses, which is expensive, too expensive. So one of the stands that some of these automobile manufacturers have taken is to keep these data in the digital format and then produce them as and when a requirement comes up locally, only by giving the drawing or 3D model of that part and finish it and give it. Even if it is 10 times or 100 times the cost compared to the inventory keeping cost, this would be much better for the manufacturer. So this is in fact already a business. We have few manufacturers from France and Singapore with whom we are working who have this as their actual business, where they take in legacy parts, obsolete parts from OEMs, they convert it into 3D models, they store the data in cloud, and they're going to be giving the entire repository at any point in time. If a specific model comes up for requirement, they're going to be managing the documents and even manufacturing or printing these parts, finishing it and offering to the customer as a complete solution. So in fact, if you see some of the logistics companies like DHL have taken this up very seriously, where they want to take up this as a solution, where they want to offer this connectivity where they can produce a part, print it and offer it in a very short time. So this is another interesting trend for the future which will come up much stronger going ahead. So we'll look at some case studies now of different parts, different examples. So this is a rear wheel hub that was done for an electric vehicle. Here we also did some topology optimization where weight reduction happened. This was for a sports car manufacturer here from an electric vehicle. This was a project that was done. Some samples that have to be made for faster fixturing tooling. This was something that was considered for automobile component manufacturer, where instead of doing it out of imagination, they ended up deciding to printing it very quickly and then putting it to use. So fixture development, your inspection plan development, all of that happens much faster, much better, instead of doing it out of design or just simulation. So this was another interesting case that happened. This was a motor housing that was printed for a startup company who was doing motors for a specific automobile case, wherein as opposed to a conventional process of either a solid block of material that was required to mill out and get this part out, or a conventional way where you'd have to wait for a long time. They prefer 3D printing as a methodology of making these or producing these parts in a much shorter span of time. So this is where you can see the part was printed, machined and given in less than 9 or 10 days time to meet their requirements. So like this time, so one has to identify what aspect of 3D printing are we leveraging on to get benefit from. So it cannot be a direct apple-to-apple replacement, but either time, effort, rejections, or some other aspect of it which is a concern can be a solution where 3D printing can become a solution. So this is one such case. This was an interesting case where an automobile manufacturer who was getting into electric vehicle manufacturing, they were exploring three-wheeler electric vehicle, and in this case they were sourcing parts from a place where they could not during the lockdown, and it's stopped their entire supply chain for their proto development phase, and they only had one set of samples that they were able to give us for reproducing them. They did not have much engineering documentation either. So in this case, what happened, we were able to reverse engineer it, recreate the entire documentation by 3D the 3D models were generated. We worked with a gear manufacturer closely to even create the 2D drawings and acceptance criteria for these. And the parts were printed, and then we even did some lightweighting. As you can see, the parts were heat treated and finished and offered to the customer as a fully finished solution, along with the engineering documentation, which helped them to go ahead and mass produce them locally in this time of crisis. So like this, the solution is much wider than what we can imagine in general. So when I say tooling, we refer to the die and mold manufacturing here. So we refer to the plastic injection mold here. This is an example where you can see from a plastic injection mold manufacturing, nearly 65% of the total cycle time is the cooling time. So this is mainly because anything that is ejected faster than what is required, the part ends up warping, which is a deformation we wouldn't want. So now the problem here is the cooling of these dies is a major concern. So using a conventional route, what happens is these dies are cooled using gun drilling, or cooling channels are created using gun drilling or deep hole drilling process, whereas with process called as conformal cooling. So what you can see on the left side is a die which is made using conventional process, where you have a long drill or a deep hole drill that is done after the die is made, and those channels are plugged to create this artificial channel of water pathway or cooling oil pathway. Whereas with 3D printing, what happens is you are able to do, you can get very close to the surface or heat generating surface to create these cooling channels by having curvilinear holes, which are not necessarily straight, but in any shape that you want, which will take the form or the actual form of the part which is being produced. So this is one of the major advantages where a lot of die manufacturers are exploring 3D printing for improvement in productivity perspective. So you can see some of the deformations are warpages and air traps and blowholes that end up coming in the plastic parts because of the non-uniform temperature distribution. And with 3D printing, what happens, you can see here, we offer uniform temperature distribution, and you can see, as opposed to the leftmost images where you have conventionally made tools, you have red zones which are high temperature zones and light blue zones which are low temperature zones, whereas with 3D printing you're able to get uniform temperature distribution, thereby improving the cooling time and also your cycle time. So 3D printing is playing a major role in die manufacturing also. So some cases here you can see what used to be a cycle time of 55 seconds was brought down to about 33 seconds, because what was conventionally made using just 4 straight holes was converted into a completely cooled design, which brought down the cycle time by 40%. And in this case, the specific customer had a savings of over 12 lakhs in this specific case. So more examples like this, where time was reduced from cooling perspective, where cycle time was reduced significantly, and customer found it very useful, either in terms of time reduction or specific feature that was coming out as a rejection. I'm sure I also understand in die casting also the rejection rates could be as high as 20-25%. Whereas with in some cases that we've seen with 3D printing, people have had much better success rates of getting aluminum die casting parts done in a better way, or much because some of those features, maybe like blowholes or specific aspects, can be cooled better, and then your part output is much better. So that's an interesting. So more cases about the dies that are done. We'll skip this for want of time. So other aspects are things like fixtures. We all use machine tools today. This is a specific case. We worked with an automotive component manufacturer in Chennai, where they were using VTLs, and we all are familiar with the concept of seat check. So anything that either has automation or critical component machining, we want to doubly ensure that the components are sitting correctly before we do a critical operation, either a milling or a boring, a boring or a very critical drilling operation. So if there are any burrs or chips that are blocking the component being a resting area, then we end up having deformations or defects and rejections. So the seat check is critical. This was a specific case where you can see a fixture part which was being imported from Germany was converted into 3D printing by this customer, and you can see that a hole which is at the bottom here, which was not in a straight line, was very difficult to make conventionally, and this was made using 3D printing and given. This was specific because the design itself was such that it could not be made in conventional way, and it had to be designed in this specific way itself for its specific application. So like this, 3D printing is not only helping in part production, but also aiding in support and equipment like fixtures and patterns in 3D printing. This is another interesting case we did as an analysis where robotic gripper arms were 3D printed or considered for 3D printing here, where it allowed a downsizing of a robot instead of going, because this could be heavy and bulky because of its shape and size, but with 3D printing, a concept was brought where it could be made much lighter, or just enough material was added so that you could choose a smaller robot size, and even the fingers are being considered to be made with 3D printing where they're very special shape and size, and they're low volume. So instead of making it conventionally, they could be made lighter and more specific to the part shape to get it more to that specific requirement. So like this, the printing can be used as support for production also, not just for production. So that's what we had in terms of the case studies. We'll just talk one slide about what we are to give you an idea. As Sir rightly said, we are Amaze Solutions. We are a joint venture between Ace Designers, the turning company, and the machining company. We are the additive manufacturing wing of Ace Micromatic Group, and we provide printing services. We've been doing that for over 3+ years, and we've been researching on the subject of additive manufacturing for over 5 years. This came to us because metal. We've been into metal cutting, and for us, metal cutting has been the bread and butter. And what was a potential disruption is what we felt about 5-6 years ago. We wanted to explore if there's any opportunity for us in the newer technology, and that led to an R&D project, and then finally ended up becoming a separate company in itself. But the long-term plan for us always has been to be able to make machines. So what led to being 3D printing services has now led to becoming a machine manufacturer. So very soon we'll be launching our own machine also. So to sum up what we offer, or what our offerings are today, we give 3D printing services, we print parts, and we do training, consultations, and AM adaptation. We can handhold people or customers in trying to understand what sort of components could be converted into 3D printing and what could be feasible for 3D printing. And we offer application engineering support, which is designed for additive manufacturing wherever required. We make metal printing machines. As you can see on the right side, that's our machine, which is a high productivity machine, which we're just launching very soon. And of course, we understand the complete ecosystem. So we offer the complete end-to-end solution around metal printing space, all the way from design to productionizing for additive manufacturing. So this is what we had to say about our company. And just to sum it up, what is the state of additive in India? So this we know one of the perspectives, though we brought out multiple aspects to give you a brief of how has India been doing on this. Additive is being used by automotive manufacturers largely for prototype development and batch production. And by energy sector for low volume manufacturing, because the volumes itself in energy sector is limited, so people find it much more suitable to switch to 3D printing here in India. I am referring to people like GTREs, the BHELs, who have been printing their turbine blades with very special shapes and internal cooling channels. So you have a very beautiful airflow. The temperatures are better, much better wear resistance. A lot of dynamic analysis are being done, and then they're being converted into this 3D printing of these energy parts. So a lot of low volume productions are happening beautifully here in India. Medical industry, very interestingly, there are multiple manufacturers who've been producing implants here in India, 3D printing these medical metal implants. And as I explained to you, there are more than 25 plus machines being used by dental implants itself here in India. And also people are printing surgical assists, which means equipment which will support in 3D printing, in production or in operations of surgeries. That is being done using 3D printing or additive manufacturing. Right now, as we speak, there are over 150 metal machines installed all over India, and interestingly, our government institutions have been playing a very pivotal role in doing research in this subject. So, over one third of these machines are located in government institutions. People like lecturers, CPREs, BHELs, and then we have DRDOs. Every lab of DRDO either has a machine or is buying a machine, and many others like this have been investing in this technology for many years. In fact, you'll be surprised if I tell you the first metal printer that came to India was 18 years ago through our CMPI, which is very much here in Pune, where we come from. So way back in 2014, 2004 is when first metal printer came to India, and they still continue to use that product both for research purpose and some small parts and small application development. So like this, some of our government institutions have been very instrumental in either developing the technology or leveraging and learning from this technology to make some very critical parts, very interesting parts today here in India. And over there are 15 plus metal service bureaus. When I say service bureau, these are companies who you can approach to make some of your parts, make some of your sample parts, who could do it. And they've been printing parts for a lot of OEMs and a lot of component manufacturers for either of these advantages that we saw earlier. So that is what has been happening. More than 15 plus metal service providers. Some of the key OEMs like Hero MotoCorp, Bajaj Auto, MRF, Honeywell, GE, etc. have already invested in metal printing equipment. They've been using it for their R&D and photo development. Other companies like OEMs like TVS, Royal Enfield, etc. have been extensively using additive manufacturing for their development from service bureaus, and they've been learning and then developing many of their new parts, new products using this technology here in India. Some of the die manufacturers have been exploring and doing some of the advanced ones have already ventured into doing their dies using conformal cooling and using high-power solutions where we've been able to save parts in plastic injection molding applications. As I said, many hundreds of plastic and polymer industry-ready machines are being used in India, where the machines are being used either for a quick sample production, sample part development, or another application where either a fixture is being made or something like that.
Hello,
And
sir, Dr. Vishwas.
yeah,
Sir, there is some background noise, sir. Your voice is not audible, sir.
okay, I'll let me see if it will get any better. Um, give me just a second. Is it any better now? Am I audible now?
No, sir, it is
Your,
still
your,
feeble, sir.
your voice is feeble actually.
Or is it?
It's
Yeah.
very
Not.
feeble.
Is it any better now? I've come to a little more quieter place. I hope this is still the same. Not audible. Hello.
No, sir, very feeble, sir.
Okay. Give me 1 second. Let me just check. I can do something about it. Apologies for the same. Is it any better now? Am I audible now?
Yeah, this is better.
Okay, okay. I'll continue. I just have one more slide and I'll finish with that. Something to ponder about is this last point of mine, which says India being one of the largest economies of the world, we are huge in manufacturing. We nearly contribute to about 4% of the global manufacturing requirement. But from an additive perspective, we are less than 0.1% of the investments compared to the global scale in additive manufacturing. So we are still lagging behind compared to many countries globally. Something to think about. Just to conclude, taking on from the previous point, additive is not just a type of manufacturing, but it's a whole new science which has opened up opportunities in multiple domains, as I explained in each of the slides, all the way from prototyping to complete full-fledged production. Today, additive manufacturing is changing the whole scenario in manufacturing. Today, it's largely being, like I said, used not just for prototype, but also in production. We ourselves are producing continuous volume, high volume production of certain parts for certain key customers today here in India. Additive also is helping production in support equipment like your tool, dies, patterns, etc. for enhancing productivity. And finally, of course, additive is also being used for fixtures and assembly, fixtures in machining, assemblies, inspection, etc. We work with customers to whom we made fixtures for inspection, we made fixtures for assembly in the whole process of manufacturing. So this is what additive has to give. So to conclude, we strongly encourage all of you to add a little bit of additive in your own manufacturing in whichever way possible. Because this is sure definitely to stay. This is a technology which is changing the face of manufacturing all around the world, but in a very slow and steady way. So that's what I had to say today. Thank you so much for your time. I hope I've not overshot the time slot that was given to me. I'm happy to take questions now.
Thanks, Dr. Vishwas. So may I now request Mr. Shiv Ganesh to take forward the Q&A session and wrap up the session, sir. Over to you, Shiv Ganesh, sir.
Yeah, thank you, Prithvi, and thank you, Dr. Vishwas. Really, as your company name is amazing, really it was quite amazed to hear the wonderful lecture. I feel that walks the talk. The experience, whatever you had gained so far within a short time, it is very, very difficult to convey to the major audience. The two variety of applications are there, and I understood that everything under the sky is possible using additive manufacturing without any exaggeration.
Great, sir. Thank you
So
so
a
much, sir.
wonderful speech by you. So now a couple of yeah, Dr. Vishwas. And before going to the audience, only one question from my side, and it is very fortunate to have you with us, who is having a very good experience in metal cutting and metal forming. And one of the slide which you had shown shows that around 150 machines are currently available in India, and almost one third is around 50 machines institutions. Whereas regarding the cutting and metal forming, since you are having a very vast and good experience in both the things, what do you feel the future scope of the usage of additive manufacturing in India? Of course, you have given the most insight in segmentation wise as well as cost economics wise and many things. Really, you are covered in a very good way, A to Z. But still, what is your view in this particular perspective? Because the 150 compared to the major requirements and major things, especially spare parts, is one of the very, very good area where we can able to see it is a need of the hour. And as we know in India, the large variety of spares is required, because when the technology is changing and when the obsolescence is happening in certain items, especially from the imports. So definitely this additive is need of the day. That is what which we feel. But what is your view comparing the metal cutting and metal forming? Maybe another 5 years. What India would do?
Yeah, it's actually a very good question. See, in fact, we got into this whole technology to explore if this is a technology that could eliminate our existence in terms of our metal cutting perspective. But today, after spending 5 years, I can very confidently tell it is not here to replace or disrupt the conventional metal cutting space, but it is here to complement it very well. 3D printing, I don't think so in any time near future in the next 5 to 8 years is not going to be replacing metal cutting. Metal cutting has its own space of manufacturing. There are a lot of things that 3D printing can definitely not do, or we don't see it doing in the next 8 to 10 years, which only metal cutting can do. But however, having said that, there are certain aspects and applications and sectors where people are finding this to be a lot more suitable compared to the conventional ones. So it is replacing those in replacing the conventional technologies in those segments, but only the volumes may come down going ahead in terms of when a customer might want to invest in, say, 10 machines to remove so much material and finish the part, they might decide to invest one or two of this machine and maybe three or four of the metal cutting machines to finish it and get the part out. This is when see, today one of the major inhibiting factors in 3D printing is the cost of the product itself, the cost of raw material, and its speed of manufacturing. So it cannot replace a conventional machine or die casting machine which can spin out few thousands of parts every day compared to this one here, compared to this. But like I said, there are applications which are calling for a fewer numbers. The batches are reducing where their volumes are still lesser. In such applications, maybe people may consider for a small types of products. So to give you one example for this, HP, who make these printers, or I mean color printers or paper printers, when they decided to get into additive, they did an exercise to find out in their own manufacturing how many of the parts can they convert into 3D. 3D printing. So they did an exercise where they evaluated more than 6,000 parts, out of which they were only able to find some 25 or 30 parts which were actually feasible for 3D printing, which actually made economical sense to be converted into 3D printing. So this just goes to show that this is not yet ready to replace it from every perspective, but for someone who's inquisitive, for someone who's willing to learn and understand and explore, this is surely going to open up doors in a many different ways. So, to give you on the other side, we all know Elon Musk and his fascination for rocket science. Today, he's actually burning rockets like firecrackers here. So every second day, there's a 10,000 crore worth of space shuttle which gets burnt out or which fails, and the whole thing goes for a toss. And there are at least about 200 metal printed parts in each of those space shuttles which are being used today, which have some of the most exotic materials, which very high temperature withstanding capability, which are being printed. In fact, when we talk about buying parts or buying machines, he talks about buying companies. He has invested in many metal printing startups, many metal printing companies, so that he gets that leverage and he produces these very exciting, very interesting parts. A lot of published information available. So such cases will definitely open doors for 3D printing.
Excellent answer, Dr. Viswas. They are really, it is somewhat motivating, really the manufacturing community to go towards the additive manufacturing, where you are well presented that it will be a complement, metal cutting and this additive manufacturing. Thank you very much. And we will leave to audience some of the questions are there. I request audience to type their questions in their chat box so that we can choose of questions because of the lack of time. So regarding Mr. Sandeep Shetty from TCAP, we had asked some couple of questions. What are the accuracies that can be achieved by 3D printing? This is one of the questions.
Sure. Sure. So I think one of my slides showed this. So today, what is available in 3D printing is something as low as plus or minus. I mean, what has been achieved by a lot of people is about plus or minus 50 microns in terms of dimension accuracy. This is largely decided by the laser beam spot size. So I'm referring to metal printing. So today, the laser beam that is being used to melt the powder is of the size of about 70 to 80 microns. So that is the one that is dictating it. So imagine a paint brush which is being used to paint a big canvas. Now we can go to a very fine paintbrush, but what will end up happening is it will take you many days to complete that painting. So there's a small compromise that one will have to do in terms of speed of printing versus accuracy of printing. So there are some small parts which need very intricate manufacturing or printing. For such parts, people choose a smaller size machine and a smaller laser beam spot size, which you can achieve something as low as 50 microns.
Fantastic, fantastic. And one of the question which is asked by Mr. Pankaj in the chat, you 3D printing for grinding finished parts. That means, I believe his question is, can we eliminate grinding? That is the way which I can understand.
No.
Yeah.
Definitely not. So finishing is something that cannot be eliminated, but everything else can be eliminated, which means maybe your poaching, your roughing, your semi-finishing can be eliminated, but your finishing cannot be. The surface finish that is achieved so far is somewhere close to 2 to 3. That's the best that we have seen in our little experience, or even from publications. What you'll see is 2 to 3 is probably the best surface finish that can be achieved using printing. That is in specific orientations and topographies, but grinding is a long shot. It will never be possible to replace that process because a lot of applications call for that kind of finish.
Okay. So grinding is essential. Very good.
Yeah.
And one of the question from one of the participants is, are you able to supply the machines for training purpose also?
Absolutely, very much possible. I mean, I'm here presenting in general for the industry, so forget us. There are wonderful machine manufacturers today who are able to make and sell these machines. We are one of them also who can produce and give you machines for training, both from a plastic, metal. If not us, we will connect you to the right company who can offer you this solution for your training purpose. We'll be happy to do that.
Fantastic. And one of the question just okay, that is a question which you had already answered. Convention technology. And another question. Okay, Mr. Ashok of TCAP, he had raised his hand also. He had asked, please deliberate on link between nanotechnology and additive manufacturing with respect to material structures.
With respect to material structure,
Yes.
so do you want me to refer to material structures and structural property
That is,
in general, or with respect to nanotechnology? That's a bit of a. I'll give you from a nano perspective what is happening today. Interestingly, there are people who are working on very tiny levels of printing. So I brought out the aspect wherein the layer thicknesses and the powder. Today we work with metal powders, or mostly printing happens with either filaments or powders. And when people work with powders, the size of these spherical powder material is anywhere between 20 to 60, 70 microns, the diameter that I'm referring to. So when we get to nano, there are people, very specialized machines and manufacturers who are working with sub 5 micron, sub 1 micron kind of materials, and that's again made through very specialized vacuum type of process or plasma atomization process, and they are using a very fine energy source to melt these parts to get into that kind of technology. In fact, one of the output market is semiconductors, which is very interesting, where people are printing semiconductor wafers of very small size, which is nothing but depositing at the atom level certain silicon or other material on a substrate plate to get your final part out. So this is at a very niche, very high-end aspect. Nobody in and around Asia is exploring this. Only few research institutes and very advanced manufacturing companies have ventured into something like this. I don't know if
Very
I
good.
answered your question, sir, but if at any point in time you can reach out to us, we'll be happy to explore further. If you don't, we can surely find more answers and give it to you, sir.
Yeah, Vishwas. I think because he's interested in learning more about the different material strength, etc. So I request Ashok to contact Vishwas in future. So there are two more couple interesting questions. So with that we will close. So one of the interesting question is, how is additive manufacturing being used in India for maintenance, specifically addition of material to worn out parts?
Yeah,
Addition
so
of material to worn out parts. Yeah, that is
yeah,
from Ravi Kiran.
beautiful. Very good question. In fact, globally itself, MRO, maintenance, repair, and overhaul is one of the biggest applications for 3D printing, where you have either worn out blades, worn out impellers, worn out equipment which come for repair. Most often than not, they have to be scrapped or thrown away. But when it's of a very exotic material like hash alloy or titanium or high grades of Inconel, it's very it's very sad to see something which has to be thrown away because of a small crack or a chip off or a wear off at some end. So 3D printing beautifully is bridging that gap where you're able to print material in those areas. There are some very interesting hybrid products, hybrid machines which are there in the industry who will allow you to print and mill out that extra material simultaneously. In fact, EMG has an interesting product. There are a couple of other manufacturers also who have products where a 5-axis milling machine has a 3D printing head which will also allow you to deposit material. So you can simultaneously deposit material and in the area where material has to be added or area has been worn out, and then you can mill it off to get that final shape and then use it for other applications. In the normal powder bed also there are people who are doing this where you have some deformations worn out. Say for example a die that gets worn out in the top of it, people are able to mill off that top area and 3D print a deposit material on top of it to get the final part, reconstruct that final part and give it at a later point.
Thank you, Vishwas. And I will post you the last question for the day.
Sure, sir.
Dr. Suresh Kohli, he had requested two questions. Of course, he is asking, he want a confirmation whether the faster product development time,
Yeah.
can you generalize it with additive manufacturing compared to CNC? We want to get
Faster
a confirmation
product
from you.
development,
Faster,
huh?
yeah, faster product development time.
Yeah.
That is when you compare with the metal cutting, that is in a CNC. When you compare with CNC with additive manufacturing, whether
Yeah.
AIM is faster product development time can be achieved.
Absolutely, absolutely. In fact, the whole technology was originally invented only for that. Only now we are seeing other advantages or other applications, but to reduce the development time is what the whole technology was introduced, where people ended up using either plastics or metals for developing their parts much faster. Because the beauty here is your entire intermediate manufacturing process or process planning is eliminated. You can straight take, in fact, you will be surprised if I tell you the most common place for a 3D printer today is in the design offices. The polymer machines are largely being used in design offices because the designer has the ability to straight away press, just like how you would go and print a paper from your desktop to color paper printer. On the same way, you can just push a 3D model into a a plastic printer or a metal printer also if required, and it can print a part. Of course, it needs a little bit of a preparation from a powder or raw material perspective, but I'm assuming all that is similar to taking care of your ink or toner or etc., where you can produce a part and you press the button and overnight your part is produced. So as simple as that. So there are people who are using this extensively for their development and prototype development. So wonderful cases, wonderful examples are there online. I strongly encourage all of you to have a look at it, read through, look at some interesting videos that are there of some examples and cases. I could not put up with everything here, but to our best abilities, we put some examples and illustrations. But we ourselves, I can assure you, you'll change AM from additive manufacturing to addictive manufacturing. You'll all get addicted to the subject, which is what has happened to us here.
Thank you, thank you. I don't want to miss this last question. Another interesting question he had asked is, can an additive manufacturing part be repaired? Be repaired. That is nothing but the previous question, I believe. Is it possible?
Yes, sir, very much possible, very much possible. The beauty about
Okay.
3D printing or the metal part that we refer to is
Yeah.
what we do is actually laser welding at a micron level. So we touch at the micron level and we do laser welding of material. So we actually go to the full melting point of the material and fuse it to form a very strong bond. So any material that can be welded can be 3D printed. So if a part has worn out, which was previously 3D printed, it's very straightforward for the same part to be brought back, and then with some small preparation, we can redeposit material on top of it and recreate that part to its original form as it was designed for.
So thank you once again, Dr. Vishwas. It is a live presentation with by hearing with a lot of manufacturing noises. Also, I believe you are in shop floor,
My
so
apologies. Yeah,
very
I'm
live.
extremely sorry for the noise
No,
and the
no, no problem.
disturbance. I
No
am in
problem.
the
It is
factory. Yes, our office is in a factory area, so it is noisy. I won't give. I couldn't stop that, so I tried
no
reducing that,
problem.
but it wasn't very
No,
successful.
no problem. But the topics and the contents, whatever which you have presented it in a short duration. Could you please switch on your video because the participant is to see your face, and
Sure.
you had well presented from evolution, geographical complexity, and then you had well presented the case studies, especially that GM seat belt, how it is evolved, and the choosing and the mass customization, types of manufacturing, and the technology, various technologies, and various materials, and excellent jargon, whatever you have used to design for additive manufacturing, and especially I enjoyed the word that is rethink and redesign. Yes. So unlearning and learning is the continuous process. And you had also excellently shared your experience with ventilator parts, which was manufactured within 24 hours, which is the need of the day, where such emergencies, especially related to medical segments, definitely it will be useful. And also bio is another interesting area. And also you had well classified the market segmentation and the landscape. Really, it is a big eye opener for all the participants. The participants are from variety, and also the on-demand components and spares. That is another interesting area. So long miles to go, and definitely such type of resource person as like you presenting to the manufacturing forum is really not only the eye opener. It will set the miles also. What we have to do, where we are, and really lot of research also we have done in preparing this presentation. That's what which we understood. So wholeheartedly on behalf of BCIC, before handing over the session to Mr. Prithvi, I thank you for accepting our invitation. And I hope many of the participants will be contacting you. We will share your contact details, and
Sure, sir.
they are very interested. And please take forward. And we wish you to continue your support in such forum. Whenever. Thank you, Doctor.
Thank you
Thank you.
all. Thank you so much, BCIC, for this opportunity. It was great for me also to interact with all of you and present to this very elite set of people. Thank you so much.
Thank
Yeah.
you, Shiv Ganesh, for this excellent moderation and summing up. As Shiv Ganesh has told Dr. Vishwas, it was a fantastic presentation that you made about the awareness where India stands in this additive manufacturing. It is it's a long, long way to go, but still we will see that it happens. And then most of the questions were all very relevant to you and then been asked. And then we hope that we could look for similar sessions to be organized in the chamber. And also, I request all the participants, thank you for joining us say the normal working hours, no, the office hours. Still, they were able to log in and had a time to participate in session. We also have posted a feedback form. Request all the participants to kindly post your feedback. That will help us to do better events, programs, and also we can look forward for your wonderful session today. Thank you, Dr. Vishwas, for this wonderful session today we had. Now, as a token of appreciation from the chamber, and also I'd like to thank Dr. Prakash for taking it all the initiatives forward. We'd like to hand over a virtual memento. We will ensure that this memento reaches your office in a due course of time. Rupa, can we have this virtual memento played? Thank you all once again. Thank you very much for joining for today's session.
Thank you.
Thanks,
Thank you so much,
Vishwas.
sir. Thank
Yeah,
you.
we'll stay
Thank
in
you.
touch. Thanks.
Thank
Thank
you.
you very much, sir.
Thanks. Thanks, you
Thank
Ganesh.
you.
Thank you.
Thank you
Thank
all.
you.
Thank you.
Thank you all.
Thank you. Thank you.